Welcome back. Good morning if you were not on session one. We're going to get going here. Thank you for participating in the MABA Great Montana Ag Rally. This is a great 1-hour educational workshop to help our membership continue to stay informed and up to speed on the latest technology and information. We want to give a thanks to Central Crop Consulting for their support of the rally and sponsoring this session. Okay, let's get going here with, we're going to start with our message from our sponsor, Central. Jeff, Joel, thank you very much. Appreciate that you guys sponsoring this session there at Central Crop Consulting. All right, let's move on to our presentation. This is going to be Soil Acidity by Clain Jones. Clain is MSU's Extension Soil Fertility Specialist and Chair of the Rocky Mountain CCA program. His research and extension focuses on nutrient management practices that improve the producer's bottom line, along with soil and water quality. Again, if you have any questions, please use the Q&A, and I will pass it on over Mr. Clain Jones. Thank you.
All All right, thanks a lot, Jake. Okay, good morning, everyone. I wish I could see you. I know you can see me, I hope so. The topic of today's talk is soil acidity in Montana. A lot of you, I don't know what percentage, but a lot of you have heard me talk on soil acidity, or you've heard my colleague, Rick Engel, who's now retired, talk on soil acidity. So today's going to be a little more focused on research results that Rick has come up with since our last presentations, which were basically last winter. And a lot of that has to do with how much lime should you apply, how should you apply it, and what kind of yield responses are we seeing to lime. If you have any questions, please enter them in your question and answer box. Or if you think of questions after today's talk, please send me an email at the address shown at the bottom of your screen, or give me a phone call. So today I want to give a very brief intro of the problem, again, because I feel most of you have heard about it, discuss lime rates, how they're developed using lab pH buffer tests, the differences between sugar beet lime and ag lime rates, show some yields after liming, and discuss pH stratification both with and without tillage, and finally some practical considerations of liming. So these show a couple photos of what acidified soils do to crops. This shows an area, the lowest pH we've recorded in Montana is pH 3.8. This is low enough that it essentially stops crop growth, as you can see in this photo. Here's another image on Durham that shows very yellow, short plants growing in Choteau County, or trying to grow in Choteau County. And then the alarming thing to me is not so much the smaller areas, but the areas right outside of those areas look pretty good. But pH 5.1 is getting very close to where we see aluminum toxicity, and we know this is probably only a year or two away from looking a little more like this soil. So soil acidification in Montana, a little bit of background. Some cropland soils are hitting a tipping point and rapidly becoming acidic. We've identified 24 of Montana's 56 counties have this issue in at least one field. The most alarming is Choteau County, where 40% of the randomly sampled fields have pHs below 5.5, so that's very concerning. The surrounding counties have less, but they still have some. We know that this process can happen pretty quickly. We don't have a great record of it in Montana because we just recognized it was a problem 5 years ago, but we can turn to our colleagues in Eastern Idaho that shows that in just 25 years, soil pHs there went from 7 to less than 6, and many have severe problems. The cause is nitrification of ammonium-based nitrogen fertilizer. The rates of drop can be pretty quick on coarse textured soil. So we've measured pH drops of 0.14 units for every 100 pounds of nitrogen per acre applied on a sandy clay loam outside of Big Sandy. We've measured a slower drop on a silt loam west of Bozeman, closer to 0.04 units for every 100 pounds of N per acre, but you can envision both of those after 20 to 50 years of nitrogen fertilization can show significant drops in pH. So just think to yourself whether or not you've seen unexplained herbicide damage, a change in herbicide action, an increase in fungal diseases, maybe N-deficient legumes, again in small spots that maybe grow each year. I'll talk a little bit about aluminum toxicity, and aluminum toxicity is the major issue with low pH, but herbicides actually can start having more carryover or less effectiveness before we see aluminum toxicity. My colleagues at Washington State warned me about that. We also might see an increase in fungal diseases well before we see aluminum problems. And then we also see pore end fixation somewhere below about pH 6. We see substantial crop losses, complete crop failure in some places, as you can envision from that introductory slide. So just as an example, looking at this figure over here for Spartan Charge, it shows that as soil pH drops below 7, that solubility really can drop, and you can envision as it goes below 6, it drops even more. Generally, when herbicides are less soluble, they're less available, and they're less effective. For some herbicides, microbial degradation will slow with lower pH. That's because microbes just don't do as well at low pH. For weak acid herbicides, the herbicide binds to the soil more strongly at low pH, and this will result in a longer rotation interval. So that results in some herbicides persisting longer than they would at neutral to alkaline pH. I have not seen differences in labels in Montana for different pHs, but if we turn to our neighbors, and I might be wrong, I'm not a herbicide expert, but when I've turned to our neighbors in the Pacific Northwest, we often do see pH on labels. So what this table shows is that for soils that have greater than pH 6.2 and greater than 16-inch annual rainfall, the rotation interval following a barley application of Beyond is about 9 months. If instead that pH is less than 6.2 or we have lower rainfall, it jumps to 36 months. Now, I know most of Montana has less than 16 inches, but this really demonstrates how big of a difference low pH can cause in rotation intervals. So you have to be more careful in these low pH areas, and also use carryover as an early indicator of low pH. So chemical degradation increases or changes at different pHs. Some degrade faster and some degrade slower as pH changes. So some herbicides become less effective at low pH. So moving on to the spatial extent, like where is pH lowest in our soils? Well, it tends to be lowest right at the surface. This figure shows as depth increases, soil pH increases. So the lowest pH areas on 5 north central Montana farms all occurs in that top about 2 to 6 inches. By the time we get down to about 9 inches, the pH is essentially neutral, and at about 20 inches, it's pH 8. So this problem is really concentrated near the surface because that's where we're applying our nitrogen fertilizer. If you talk to producers that have this problem, they will tell you they wish they started preventing it decades ago, because the cost of fixing it is very expensive and they're losing large amount of yield. So prevention is key. Anything you can do to increase nitrogen use efficiency, splitting application, soil testing, applying nitrogen closer to when it's being used, including legumes and perennials and rotation, will increase end use efficiency. But again, today's focus really is liming. If you're more interested in prevention, I have a lot on my website. I'll show you the link to that on my last page. Today, I'll cover rate calculations, application, and also yield response. Okay, so how does lime counter acidification? Some people think it's the calcium. The calcium helps buffer pH, prevent future pH change, but it doesn't bring up the pH. So it's the carbonate and calcium carbonate that increases the pH. I apologize, it's before lunch and I'm showing some chemical equations. I'm sure I would apologize after lunch too, but basically I just want to show how calcium carbonate interacts with water to form calcium, bicarbonate, and hydroxide. And as you hopefully remember, hydroxide is what neutralizes acid and results in calcium plus bicarbonate plus water, which is neutral. So again, it's the carbonate that ends up providing this hydroxide, which neutralizes the proton, the H plus or acid. And again, the calcium doesn't hurt, it buffers future pH drops. So there are liquid lime products out there. Some use the term kind of loosely, liquid calcium, liquid lime. You really need to be careful what you're buying or selling because if there's not an oxygen compound in there, like carbonate, hydroxide, or calcium oxide, it won't reduce acidity, meaning if it's, say, calcium chloride, there will be no change in soil pH. So how would you calculate lime rates based on MSU studies? My colleague Rick Engel ended up thinking, well, hey, different labs use different soil pH buffer tests. Which ones work the best for Montana soils? So he tested 4 different ones, one called the modified Malick, Adams and Evans, Woodruff, and Socorro on 10 different low pH soils in Montana. He also did some field trials using sugarbeet lime to correct soil acidity. 3 on-farm strip trials in all. I'm going to show the results of both those incubation studies and the field trials. So these incubation trials are done by taking these soils, putting them in a soil water slurry, spiking them with lime at 6 doses plus water, and then incubating those soil water slurries for 90 days and measuring pH for those different lime rates. We define the incubation lime requirement for a certain pH, and the one I've used for at least this presentation is a target pH of 6, meaning above an area where we'll see problems, at least for some time. And then we contrast the lime requirement predicted by these buffer tests with our actual lime requirements to see which ones do the best. So this is what a lime incubation result looks like. We have incubation lime rates on the x-axis, soil pH on the y-axis for our 10 different soils. You can see that there's a large range in how much lime was required for these different soils, largely dependent on what the initial pH was, meaning this soil that had a fairly high pH, 5.8, only required maybe, I don't know, half a ton per acre of lime. This low pH soil, 3.8, had required somewhere around, looks like maybe 4 tons per acre of lime. So a very large difference in lime requirements. So which of these buffer tests did the best? First, I start with Socorro. The x-axis, I've plotted the buffer test, tons of calcium carbonate per acre need versus the measured in our incubation study. How much did we really need? And what we found was Socorro did not do very well. We'd want these points to fall along this 1-to-1 line, and they did not, which is interesting because my colleague Amber Moore at Oregon State just tested Socorro, worked quite well on Oregon soils, just not on Montana soils. The Adams and Evans test did substantially better. The Woodruff test didn't do too bad, except I would have liked to see a slope closer to 1. And the one that did the best was the modified Malick test. So what I like about it is if we look at this y equals mx plus b equation, the slope is very close to 1, which is what you'd like to see, and there's not very much scatter around that point. One issue with these different lab tests is when you send soil to a lab, the labs can vary among each other and then also within the same lab. So my colleague Bob Miller sent blind soils to a number of different labs and found that lime rates that were estimated for those soils varied fairly widely, even for the same lab. The other issue is that the only labs that Bob and I are aware of that use the modified malic are mainly on the East Coast. So you would have to ask your lab, do they do a modified malic, and would they be willing to for your soils? Another approach that some of my colleagues don't really agree with is using just initial pH as an indicator of how much lime do you need. What I've plotted here is soil pH on the x-axis and the lime needed to reach pH 6 in tons of calcium percarbonate on the y-axis. What we found was that there was a very good relationship between initial pH and lime requirement, except for this one soil that had the finest texture of our 10 soils in the study. So with that outlier, we don't have a great R squared, but without that outlier, we have a pretty good R squared of 0.7. So the reason my colleagues don't agree, and I kind of agree with them, is we know soils differ in their ability to buffer pH change. And so just initial pH really shouldn't be a great indicator. But maybe in our Montana soils that have relatively similar organic matter, relatively similar soil texture, maybe that's why we have a fairly good relationship. And to me, it's a lot easier. Everybody knows their soil pH, not everybody knows their pH buffer test. So moving on to the field, a little more real life than a beaker with water and soil being stirred. So this was done on 3 farms at up to 5 different lime rates, 0 up to 4 tons on one farm and 0 up to 6 tons on the other 2. The lime was incorporated, the sugar beet lime was incorporated with tillage on 2 farms, and it was left on the surface in a no-till situation on the 3rd farm. This shows on lentils, this shows how dark green the limed areas are, and the pH was able to go up to close to 6 in the limed areas, and it remained at 4.7 on the unlimed areas. So really dramatic image of how important lime is and high pH is for helping with nitrogen fixation. These were just simply chlorotic lentils compared to dark green lentils. How did the pH change over time? So here I show on the x-axis sugar beet lime in tons per acre. Soil pH change from the 2017 pH. In the first year, 2018, we see a nice kind of linear response at low pH, and then it starts plateauing a little bit more at higher pH. And then by 2019, the pH had actually gone up a little bit more. So pH is slow to change, at least with sugar beet lime, but we did see some really nice pH increases. The initial pH was somewhere around 4.7. If we think about a target of pH 6, we would need to raise the pH by 1.3 units to get it up to pH 6, and that would require about 2.5 tons per acre of sugar beet lime. So maybe instead of using those more involved pH buffer tests, which are done in a laboratory, this might just be a ballpark number for those of you who have clients with low pH.
Got a question for you, Clain.
Please.
What depth are you sampling for pH?
So we are sampling different depending on the study. You know, you saw the stratification, we went as deep as 20 inches, but for most of our work, we are sampling in the top 6 inches, and we usually break that into a 0 to 3 and a 3 to 6. Some of Rick's work, he focused on the top 4 inches. And in this particular study, this was to pH 6, or sorry, this was based on 4 inches. We then converted everything to 6 inches just because we felt that would be more relevant to most producers, and we are seeing low pH down to about 6 inches. So if I convert these numbers over to calcium carbonate, because you might be purchasing ag lime, what this converts to, the 2.5 tons of sugar beet lime per acre to raise 1.3 units pH to pH 6 in the top 4 inches, a lot of numbers there, works out to be about 1.5 tons of calcium carbonate per acre per 1 unit pH for that top 6 inches. This is an aerial image that really shows in that study where we applied 0, 1, and 2, and 4 tons per acre of sugar beet lime. Really shows, and this was on Durham in this past year in 2020, it really shows the dramatic effects of lime. So if you look at all of the 4 ton per acre strips, the crop looks substantially better than on the side where we have 0 tons per acre. 2 looks somewhat better, 1 not as good, but definitely the big impact is going from 0 to 4. So how did that lime affect crop yields? Well, yellow pea up in the pH 6 range where the 4 ton per acre lime was applied grew about 32 bushels. Where there was a really dramatic drop in yield was going from about 6 to 5.8, which agrees with the literature that shows somewhere in that range is where end fixation really starts falling off. And then the yield didn't really change below that. So my impression is pea is fairly tolerant. Rhizobia that fixed the nitrogen is not very tolerant. Let's contrast that with durum. So in 2020 on the same field, durum was growing about 50 bushels per acre in these limed higher pH soils. But by the time we got down to about 5.5 or 5.2, the yields had dramatically fallen off compared to peas, which had a really dramatic drop and then plateaued. So durum seems to be quite intolerant and caused about, this low pH caused about a 15 bushel per acre drop in yield. One thing to keep in mind is you might not detect visually these low pH spots in the mid 5s, but it's just a little below mid 5s where we start seeing some pretty dramatic yield drops. So kind of like the equivalent of hidden hunger, this would be like hidden toxicity, where that's why you really need to get out there, scout, and soil sample. One question I'm getting a lot from producers and CCAs is how long does lime last? And we're not able to answer that question yet in Montana because we just started liming fields in the last few years. So I turned to my neighbors to the north in Saskatchewan, where in the mid 1960s, these researchers applied 3 different rates of lime: none, 2.7 ton, and 4 ton of calcium carbonate per acre. And then they tracked soil pH in the top 6 inches. What they found was that 2.7 tons of calcium carbonate per acre brought the pH up quickly, and then it still was above the initial pH 27 years later. So it looks like lime can last a fairly long time. At the higher rate, the pH stayed above 6 for essentially the entire study. So a higher rate can last even longer. So that's good news for producers who are thinking about the high expense of liming and wondering, is this only going to last a couple of years? In the Midwest, they lime about every 2 to 5 years. Here, I'm thinking we can probably go a lot longer. How did that lime affect yields? Well, the 4 ton calcium carbonate per acre always grew more than the 2.7 ton per acre, which always grew more than the 0 ton. And some of these yield increases are dramatic, meaning on the order of 10 to 20 bushels per acre more in some years than the control. So how does that pencil out economically? If you're talking to a producer, they're going to want to know, is this going to pay off or not? So here I've put in a table the different yields: 22 bushel in the control, 27 on average in the 2.7, and 32.5 in the 4. Total yield works out to be pretty dramatic differences between 0 and 4. Total revenue, assuming 436 per bushel, worked out to be about $500. And the cost of lime at that $50 per ton didn't really dig into that overall net revenue very much. So the net revenue per acre went up about $100 per acre over the whole study for the low rate, and closer to about $300 per acre for the high rate. So it's hard to get a producer to think out 27 years. It's hard to get them sometimes, of course, to think out, a few years. But if they can work with a banker and show evidence like this, I think they can justify applying lime. And I think if we had looked at these results differently, I believe the lime would have paid off in a much shorter period of time. I just wanted to show over the course of the study how dramatic the effects were.
Clain, we got a question when you're ready.
Yes, please.
The question is the length of lime effectiveness. Is there a difference between irrigated and dry land?
Yes, there would be. And so that is one reason why in the Midwest it doesn't last as long. The calcium carbonate dissolves faster, and that carbonate can leach. In our 12 to 15-inch rainfall zone, it's simply not going to leach in decades. But irrigated would be more similar, right, to the Midwest, and so it will last less long in irrigated for two reasons. One is there's more nitrogen applied. That nitrogen is producing acidity, which is counteracting the lime. The other reason is some of that carbonate and the bicarbonate will leach out of that important shallow root zone. Good question. So how much should you apply? Well, based on our field trials in a clay loam, we estimate that you should apply about 1.5 tons of calcium carbonate per acre for each pH unit increase. So if your producer wants to increase the pH from 5 to 6, you probably need about 1.5 tons of calcium carbonate per acre. If they want to go up to 6.5, it's going to take a little bit more. You're not going to need as much in a coarse sandy soil. You're going to need a little more in a clay soil. So let's just run some numbers here.
Clain, I got a couple more if they fit in.
Please.
All right. Do any nitrification inhibitors prolong the pH decline? Products, like ESN or...
Right. So ESN is a coated product. The nitrification inhibitors like nitropyrin and DCD, they have the potential to, if less nitrogen is applied. So if the assumption is that they will increase nitrogen use efficiency, then they should help if you back off on the nitrogen. Because they don't stop nitrification, they won't really slow the process, meaning it's still going to happen. Instead of happening in 2 weeks, it maybe happens in 4 weeks or 6 weeks. So it won't completely eradicate the problem. It just might increase nitrogen use efficiency, but it would have to be coupled with a backing off on the rate. What was your second question?
The second, you answered it both, but I do have another one here. In these studies, was there a change in nitrogen application processes, such as less nitrogen applied?
No. So in both the Saskatchewan study, they just went forward with typical soil testing and same agronomic practices. And in our studies, we let the producer pick his or her nitrogen rate. And so nitrogen was not altered from standard practices. Good questions.
Okay, I don't see any more right now.
Okay. So just running some numbers here to get you a flavor of how much sugar beet lime you might need to add to a farmer's field. If we go with this calculation, it's going to take about 2.25 tons of calcium carbonate per acre to raise the pH from 4.5 to 6. Sugar beet lime is only about 60% calcium carbonate. So that means you're going to need about 3.75 tons of sugar beet lime per acre to raise the pH from 4.5 to 6. Typical semi-truck trailer load is somewhere around 23 tons of sugar beet lime. So that's only going to treat about 6 acres. To give you a flavor, how many semi-truck trailer loads you're going to need and the rough cost, $145 per acre. Now, again, this gives producers sticker shock, especially if they're comparing it, say, to fertilizer rates. But fertilizer is an annual input. Lime really should be treated as a capital input because it's going to last on the order of 15, 20, 25 years based on our studies and Saskatchewan studies. This huge volume and huge weight that's needed really, and cost, really demonstrates why site-specific application of lime, I believe, is far more important than site-specific application of nitrogen. You do not want to be applying lime on a pH 7 soil. You'll probably actually hurt yield. You only want to be putting lime on the lowest pH soils. These aerials and NDVI images really demonstrate how different pH can be and how different growth is across a field. And so it really shows on this field. This is a safflower field up by Big Sandy. You could save a lot of lime costs by only applying lime in the areas with the lowest pH. This aerial image here actually is from one of our studies that shows different growth in these strips. And then this NDVI image really shows dramatic differences that are mainly attributed to pH. The other thing you're going to want to do is, if you use aerial image from Google Earth to a drone image, is to do some ground truthing to make sure that poor growth areas are due to low pH and not something else, like a seeding issue, a ridge, a herbicide issue. So one big question is how far down can lime move if the lime is not tilled? So this was work done in Washington State, looking at different amounts of fluid lime in pounds per acre from 0 up to 2,000 pounds per acre, and also dry sugar beet lime at 2,000 pounds per acre, a ton per acre. On the y-axis, I've plotted soil depth. On the horizontal axis, soil pH. What it shows is near the surface, as you'd expect, the pH was dramatically improved at these higher rates. Down here at essentially the seeding depth, there were some significant differences, but they were a lot less because lime doesn't move very readily. So there was higher pH at these higher rates and lower pH at these lower rates. Below that, there was no difference in pH. So we're really not affecting the pH down further in the root zone. Looking at a couple other studies, one in our neighbors to the north in Alberta, they found that it took about 3 years to affect the pH in the 2 to 4 inch soil zone. In a study in a wetter environment in Virginia, so maybe more similar to some of our irrigated environments, it took 8 years to affect and improve the pH in the 0 to 4 inch zone. So again, lime moves very slowly, especially in our environment.
Hey, Clain?
Yes.
I think I got a question here that probably ties in what you just talked about. It kind of goes back to the earlier question. On the liming length, how long do you think liming will last in an irrigated field?
In an irrigated field, I would guess maybe about a third, maybe about a third of what we're thinking in these longer studies. So that's a study in Saskatchewan where it looked like it lasted at least 27 years. I'm guessing on an irrigated field, maybe closer to 10, but it will really depend on the soil texture, the nitrogen rate, and how much irrigation water is applied. So those other studies were done out of Montana. This study was done in Montana by Rick Engel, looking at the differences in pH improvement from liming between a tilled system and a no-tilled system. So At the beginning of the study in year 0, these dark lines show how pH was stratified. So it was fairly similar, where the pH was very low at the surface, below 5, pretty low at 3 inches, and then went up beyond that. In the tilled field, the pH improved dramatically at 3 inches down, up to about pH 6. And this is the depth that we probably really want to affect, because it's the root zone of that, kind of wimpy seedling. In the no-till environment, notice at 3 inches, there was no change in pH, and this was after 2 years. And so even though those of you who know me know I'm a no-till advocate, we all know there's some large advantages of no-till. One disadvantage is that lime simply will not improve pH at depth in a no-till environment, at least after 2 years. One other concern, we hear from producers is they don't want to destroy their soil organic matter by tilling in lime. So Rick addressed this by looking at soil organic carbon both pre-tillage in 2017, post-tillage in 2018. And what he found was actually a perfect one-to-one line where it didn't really matter so much the depth. What he found was that a one-time tillage does not reduce soil organic carbon. Now, it might hurt other things like aggregates, but it did not hurt soil organic carbon. So one-time tillage might not be that detrimental. However, we know you have producers who won't till. So what are their options? One would be prill lime, putting it down with the seed. One would be seed placing phosphorus. I have a fertilizer fact sheet out showing that seed placed phosphorus can really improve yield, though it doesn't increase pH. And other options might be, really stressing prevention. If you have producers who simply aren't going to till in lime, they really then need to focus on prevention, or maybe liming well before they see a problem. So
you
this,
take a question, Clain?
Yes, please.
All right. If you till up your calcium carbonate layer you currently have in your soil, is this a one-time event, or does that layer somehow come back over time?
Good question. So what will happen is some of that calcium carbonate will leach, back down, especially in our wetter environments. But for the most part, that calcium carbonate will neutralize acidity in the surface. And then that calcium carbonate layer at depth will be smaller. And then you'll have to do it again down the road. The problem I see with using your existing lime, say it's at 6 to 12 inches, and tilling that up into the surface, is that you create, over time, you're going to create a bigger area of low pH, and eventually that calcium carbonate will be gone. Now, when you go to lime the surface, you have to till to a much deeper depth. So it's certainly a strategy, and there is all that kind of free lime down there. The producers in Choteau County who have tried this say they see an improvement in yield first year, second year, and they've told me by about 3 years, the problem starts getting worse again. So it's kind of a short-term solution.
How about another one?
Okay.
Can liquid lime be used to cure the pH just as fast as the dry? Generally, how much of a rate, gallon per acre, through a sprayer would be required? Would you stream it? So it's kind of a 3-part question there for you.
Right. So if we think about pounds of calcium carbonate per acre, liquid and solid should behave about the same. And I showed that study from Washington State where 2,000 pounds of calcium carbonate as sugar beet lime or as fluid lime behave very similarly. So that was the first one. The gallons per acre, that's probably one we should talk on the phone or by email, because it will depend on how much lime you can get in solution. And I won't be able to do those calculations in my head very quickly. And then the third question was, should it be streamed or broadcast? I would say probably broadcast, because you want the entire root zone to have higher pH. If you stream it, you're going to end up with areas that are high pH and then areas right to the side that are low pH. Did I get all the questions there?
I believe you did. Thank you.
All right. So looking at another study from Washington State in no-till, where they wanted to see how far does lime move over time, kind of similar to Rick's study. Here they looked at no lime in the blue bars at 6 months after and 18 months after. So there was just some natural variation in pH, which we see all the time. Then they did sugar beet lime after 6 months. Notice that the pH was pretty high near the surface after 6 months, but not very high down at about 1.25 inches, really no different than the control. By waiting 18 months, though, the pH had begun to go up at 1.25 inches. It had begun to go up at 2 inches, no change at 2.5. So again, in a no-till system, lime will move. It's just you need a lot of patience. There's also work that shows applying lime with organic materials can speed the rate that lime moves down. Again, farmers can seed place their phosphorus. They can include legumes in rotation. These are other options if they simply do not want to till. So in summary, soil acidification is localized, but it can happen pretty quickly. The modified Malick buffer pH test seems appropriate for Montana soils, but we actually have a little more confidence in our field trials just because it's a real environment. And there we find about 1.5 tons of calcium carbonate per acre should be applied to bump the pH by 1 unit. Variable rate really makes economic sense. You can use aerial images and ground truth. Both forms of lime, both forms of solid lime, sugar beet lime and ag lime, is best incorporated to increase pH in the root zone. An annual alternative to tilling is seed placing phosphorus, which I have in more details in my fertilizer fact 79, or using prilled lime, which is the most expensive lime source. And it really comes down to prevention is key, and increasing nitrogen use efficiency, using more pulses, anything you can do to avoid, I guess, overuse of nitrogen. And with that, I finish with a photo showing limed yields versus not limed yields all the way back from 1926 in Oregon, to show that even though this is a fairly recent problem in Montana, it's not a recent problem in the West. I include a link to my webpage that has more information on acidification. Any questions?
Thanks, Clain. Yeah, it looks like we got one here.
Okay.
Your cost per acre numbers did not seem to include application cost. Do you have a feel for what custom applicators are charging per acre to make a lime application?
Yeah, we have included those. I might not have shown that explicitly here, but what we've been using based on talking with a few people is about $12 per acre. And there's only, I only know of 4 lime spreaders in the state. Some are owned by private farmers. And so that I don't think that the business has really developed where somebody could maybe quote you a direct rate. But I would talk to, there's maybe the co-op in Fort Benton. I know they have variable rate applicator, but somewhere probably in that $10 to $15 per acre, which is still small compared to the, say, $35 per ton to haul sugar beet lime from Billings up to, say, Choteau County.
Okay. Next question. Is there a quick calculation to determine how much seed placed phos would make a difference between 5 and 6 pH, even if it's a temporary fix?
No, to answer your question. So Rick only did his phosphorus study on Durham in 2 sites. And what he found was that there was a dramatic increase going from 0 to 15 pounds of P2O5 per acre. Now, a lot of no-till farmers are putting on 15 units or 25 units. And so in a way that might be masking the problem, where we don't really know we have a problem until 1 year they don't apply phosphorus. Where he saw his best yield was up at 60 units. So that's getting to be a pretty high rate, but we don't have enough studies to really show would you need, say, less in a higher pH environment. So unfortunately, it's going to be a little bit trial and error.
Is there any more questions? Okay, so we're going to have the recording, just a reminder, recording will be available on the MABA YouTube channel and the MABA website later in December. Okay, so in closing, we just want to thank Clain Jones. Appreciate your time. Again, if you have any questions you think of afterwards, feel free to reach out to Clain, or you can go through us or whatever you need to get with him. Just want to thank you for joining us this morning for our first two sessions for the Great Montana Ag Rally. We hope you found this session to be informative and helpful. Again, thank you to our speakers. Thank you to Central Crop Consulting for your support and sponsoring this session too. So next, we're going to have the next session for the Ag Rally is going to be held on December 15th. Session 1 is going to be Field Technology by Ryan Helmer with Wilbur Ellis. He's just going to cover, the history of field technology, where we're at currently with it, and the future direction, where we're going. In session 2 will be Problems in Chem Fallow, presented by Dr. Phil Westra, professor and extension specialist with Colorado State University. So please join us December 15th. I hope everybody enjoyed. Once again, thank you to our sponsors, thank you to our speakers, and everybody have a safe, wonderful week. Thank you.